Hello students, welcome in the next lecture of integral equation. Okay, so in previous lecture we see the method for finding the solution of freedom integral equation of second kind. We see the method, that is Adomain decomposition method. Okay, so today we are going to see the another method for finding the solution of freedom integral equation. This method is used when the function f of x, that is, if we consider the freedom integral equation of second kind, we know that the standard form, that is u of x is equal to f of x plus lambda integration from a to b k of xt into u of t dt. This is the standard second kind freedom integral equation. Here this function f of x, if this function f of x is complicated function, then for finding solution of this type of integral equation we use the modified Adomain decomposition method. In that method we split this function f of x into two parts and relation to find this values u0, u1x up to dash dash dash, and then we consider the solution of this integral equation in the form of u of x is equal to summation n is equal to 0 to infinity un of x for n greater than or equal to 0. Okay, then we see modified Adomain decomposition method. Adomain decomposition method. Okay, so first we write here the freedom integral equation of second kind, that is, we know that the form u of x is equal to f of x plus lambda integration from a to b k of xt into u of t dt. We take it as equation number first. This is the standard freedom integral equation of second kind. Okay, so here we consider solution of equation 1. Solution of equation 1 is u of x is equal to summation n is equal to 0 to infinity un of x, where n greater than or equal to 0. We consider the solution of this equation, which is u of x, that is the addition of infinite terms of un x for n greater than or equal to 0. Okay, so we take it as equation number 2. Then the function f of x in equation 1. Equation 1, if this function f of x is complicated, then we use modified Adomain decomposition method, and if the function f of x is a simple function, then we use, that is, Adomain only decomposition method. Okay, so in that method we have to split f of x into two parts. Okay, so we consider, that is, f of x is equal to f0x plus f1 of x. Then put this value f of x is equal to f0 of x plus f1 of x and this equation number 2 in this given equation 1, that is, put f of x and equation number 2 in equation number 1. Before that, we can write this u of x as u of x will be, we can write u0x plus u1x plus, we write in splitted form u2x plus up to dash dash dash. If we put f of x, value of f of x will be f0 of x plus f1 of x, and this equation number 2, that is this equation, in equation number 1, then equation number 1 becomes, in LHS we have to put this value, we get u0x plus u1x plus u2 of x plus up to so on dash 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 is equal to f of x is equal to, we can write this f0x plus f1x, that is equal to f0 of x plus f1 of x plus lambda will be as it is, integration from a to b kernel k of x t, and instead of this u of t we have to put these values, that is if we consider this u of x in terms of t, then we get u of t is equal to u0 t plus u1 t plus u2 t plus up to so on. Okay, so we put in RHS, that is k of x t in bracket, we get here u0 t plus u1 t, u1 of t plus u2 of t plus up to dash 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 into dt. Okay, so we simplify this RHS, we get LHS will be as it is, u0 of x plus u1 of x plus u2 of x plus up to dash 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 is equal to, that is plus up to so on, is equal to f0 x plus f1 of x will be as it is plus lambda integration from a to b k of x t into u0 of t dt, that is we separate this integration, we get first term lambda a to b k of x t into u0 of t dt plus lambda integration from a to b k of x t into u1 of t dt. Okay, plus lambda integration from a to b k of x t into u2 t dt. Okay, plus up to so on. Okay, so we can, here we can assign the value u0 of x is equal to f0 of x and u1 of x is equal to f1 of x plus lambda integration from a to b k of x t into u0 of t. Then we get the runs relation, that is to find components u0 x comma u1 x comma up to so on, we assign u0 of x is equal to f0 of x, then assign u1 of x is equal to, this u1 of x is equal to f1 of x plus, from this equation lambda integration from a to b k of x t into u1 of, into u0 of t dt. Okay, so next u2 of x is equal to, we assign, we get this term lambda integration from a to b k of x t into u1 of t dt. Again if we consider here next term, then we get here u3 of x is equal to lambda integration from a to b k of x t into u2 t dt. Okay. Then we get from this and up to so on. Okay. Then we write the general formula. Then we write the general formula that is we get set first u0x is equal to f0x, then u1x is equal to f1x plus lambda integration from a to b k of xt into u0 of t dt, and all other terms are we have to get by using recurrence relation un plus 1 of x is equal to lambda integration from a to p k of xt into un of t dt for n greater than or equal to 1. Okay. So by using this formula we have to get the next terms of or next components, that is u2x, u3x and up to so on. Okay. So in modified Adomain decomposition method, first split the given function f of x into two parts. We name it as f0 of x and f1 of x. Then assign u0 of x is equal to f0 of x and u1 of x we can find by using f1 of x plus lambda integration from a to b k of xt into u0 of t dt, and all other components, that is u2x, u3x and up to so on, we can find by using this recurrence relation un plus 1 of x is equal to lambda integration from a to b k of xt into un of t dt. Okay, for n greater than or equal to 1. So we consider here example on this modified Adomain decomposition method. Okay, and also note that here in most of the examples we have to only find the two components, we have to need to only find the two components u0 of x and u1x, and all other components are getting 0 in most of the examples. So we consider the first example, example number 1. Consider the Friedel integral equation. Here we consider this integral equation u of x is equal to e raised to 3x minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus integration from 0 to 1 x into t u of t dt. Okay. So first here we compare this equation with the standard Friedel integral equation of second kind. So first compare given equation with standard Friedel integral equation of second kind. We know that the standard Friedel integral equation is u of x is equal to f of x plus lambda integration from a to b k of xt into u of t dt. If we compare this equation with this equation, we get f of x will be equal to here this e raised to 3x minus 1 by 9 in bracket 2 raised to 3 2 e raised to 3 plus 1 into x. Okay, then lambda will be equal to, here coefficient of this integral will be 1, that is lambda is 1, and limits are a is equal to 0 and b is equal to 1. Okay, and the kernel k of xt is equal to this x into t. We use modified Adomain decomposition method to find solution of given equation 1. Take given integral equation as equation number 1. Okay. Then we consider solution is u of x is equal to summation n is equal to 0 to infinity un of x for n greater than or equal to 0 be the solution then we split f of x into two parts. That is f of x is equal to, we consider f1 of x f of x is equal to, we consider f0 of x plus f1 of x. We have to given here f of x will be this. We write here, that is e raised to 3x minus 1 by 9 in bracket 2 into e raised to 3 plus 1 into x is equal to f0 of x plus f1 of x. Okay. So here we take f0 of x. f0 of x is equal to e raised to 3x and f1 of x is equal to, we take this remaining function, that is remaining part of f of x minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x. That is, we split this function into f0 and f1 as f0 is equal to, we consider e raised to 3x and f1x will be this remaining function. Okay. Then we find components u0 of x comma u1 of x and up to so on by using modified Adomain decomposition method. First we consider or assign u0 of x is equal to f0 of x is equal to, f0 of x will be e raised to 3x. Okay. Then u1 of x we can find by using the recurrence relation, that is f1x plus lambda integration from a to b k of xt into u0 of t dt. Okay. We put here values of f1x and u0 of t. We get f1 of x, here we consider this minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus lambda will be 1, integration from 0 to 1. K of xt will be x into t, u0 of t. Here we consider u0 of x will be e raised to 3x. Then from that we get u0 of t is equal to e raised to 3t. We put here, that is into e raised to 3t dt. Then we solve this integration, we get minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus, here this x is constant with respect to t, therefore we take outside from integration, and in integration remaining terms are integration from 0 to 1 t into e raised to 3t dt. Okay, then we find this integration by using light rule, we get integration is, that is u1 of x is equal to, we get minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus x will be as it is. Then we take integration of t into e raised to 3t will be t as it is, integration of e raised to 3t dt minus integration of e raised to 3t dt. Then derivative of this t with respect to t again into dt, bracket complete. Okay, then this simplify this, we get minus 1 by 9 2 e raised to 3 plus 1 into x plus x in bracket t, integration of e raised to 3t will be e raised to 3t divided by 3 minus integration of e raised to 3t will be again e raised to 3t divided by 3 and derivative of this t with respect to t will be 1 into this dt, bracket complete. Okay, then is equal to minus 1 by 9 2 e raised to 3 plus 1 into x plus x t e raised to 3t divided by 3 minus again integration of this e raised to 3t will be e raised to 3t divided by 3 and into this 3 will be 3 into 3 will be 9, integration from 0 to 1. Okay, then we put here limits, we get minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus x. By putting limits we get here t1 that is 1 into e raised to 3 into 1 that is 3 divided by 3 minus e raised to 3 into 1 3 divided by 9. Then again we put here lower limit, that is minus, here t is equal to, if we put 0 then this term becomes 0, that is we get here minus 0, then minus minus becomes plus, and again if we put here t is equal to 0 we get here t 3 into 0 divided by 9. Okay, then is equal to minus 1 by 9 2 e raised to 3 plus 1 into x plus x in bracket, here we get e raised to 3 divided by 3 minus e raised to 3 divided by 9, this will be 0 plus e raised to 3 into 0 will be 0, e raised to 0 will be 1, that is we get here 1 by 9. Then we simplify this bracket, we get is equal to minus 1 by 9 2 e raised to 3 plus 1 into x plus x. Here we take denominator 9 and then we get here 3, we multiply this first term numerator by 3, we get 3 e raised to 3 minus e raised to 3 plus 1 divided by 9 is equal to minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus x in bracket 3 e raised to 3 minus e raised to 3 will be 2 e raised to 3 plus 1 divided by 9. Okay, then again we simplify u1 of x is equal to minus 1 by 9 in bracket 2 e raised to 3 plus 1 into x plus x. We multiply this x inside the bracket, we get x into 2 e raised to 3 by 9 plus x by 9. Again we multiply this minus 1 by 9 inside this bracket, we get minus 2 e raised to 3 and into this x divided by 9 minus x by 9 plus 2x e raised to 3 divided by 9 plus x by 9. Okay, so if we observe here, we get here minus x by 9 plus x by 9 gets cancelled and again minus 2x e raised to 3 by 9 and this plus 2x e raised to 3 by 9 gets cancelled and we get here u1 of x is equal to 0. So we get the first and second component will be u0 of x is equal to, we take e raised to 3x and u1 of x. By using modified Adomain decomposition formula, we have to get u1 of x is equal to 0. And from that, by using recurrence relation, un plus 1 x is equal to lambda integration from a to b k of xt into un of t dt for n greater than or equal to 1. If we find the next components, then we have to get all the components are 0, because if we put here n is equal to 1, then we get here u2x is equal to lambda integration, lambda will be here 1, integration from 0 to 1, k of xt will be x into t, and here u1 of t dt for n is equal to, right here for n is equal to 1, we get this formula for u2 of x. Then here u1 of t will be, u1 of x will be 0, u1 of t also we get 0, that is 0 to 1 x into t into 0 dt, then we get u2 of x is equal to 0. And again if we put u2 of x in next, that is for u3 of, for finding u3 of x, then we get again u3 of x is also 0, that is we get all other components are 0, that is we get un of x is equal to 0 for n greater than or equal to 2. Also u1 of x will be 0, so we can write here greater than or equal to 1. Okay, then we write the solution of given integral equation 1 as by putting all values of components u0 of x comma u1 of x plus up to so on in equation u of x is equal to summation n is equal to 0 to infinity un x. We get solution u0 of, we can write it as u0 of x plus u1 of x plus u2 of x plus up to so on. That is we get u0 of x will be e raised to 3x, u1 of x will get 0 plus u2x will be 0, and all other terms are also we have to get 0. So we get here u of x is equal to e raised to 3x is a solution. Of given Friedel integral equation 1, Friedel integral equation of second kind. Okay, so in this way we can find the solution of Friedel integral equation by using Adomain, modified Adomain decomposition method. So in that method, first we have to split the given function f of x into two parts. Then by using the formula or the recurrence relation, that is we have to first set u0 of x is equal to f0 of x, then find u1 of x by using formula f1 of x plus lambda integration from a to b k of xt into u0 of t dt, and all other terms by using recurrence relation un plus 1 of x is equal to lambda integration from a to b k of xt into un of t dt. And by finding all these components, we have to put this component in infinite series, and by solving that or by using Taylor's expansion or in sum of infinite geometric series, we can get the solution of the given integral equation. Okay, so thank you.